All right, so we're not learning any more tests of convergence or divergence, which I'm sure you're very happy about. We have covered all of them. Today, we're going to look at whether a series converges absolutely or conditionally. So we're going to use some of the other tests that we've done and use the ratio test actually for a lot of these. Actually, I think we're going to do the ratio test for all of them. And I wrote it on here for you. If the absolute value of the series converges, then not putting the absolute value there, like the series itself, will also converge, and the series is absolutely converging. So if you look at the absolute value and it converges, it's absolutely convergent and you're done. If you look at the absolute value and it diverges, it can still converge conditionally if the series itself converges. So if you get that the first one diverged, you still have to look at it without the absolute value and see if that converges. So that's like a two-part problem. Okay, so let's look at the first one. I made the first one pretty easy. If you do the nth term test for this, you would do limit as n goes to infinity of n factorial over 2 to the n. And it really doesn't matter if you're looking at the absolute value of this or the series itself, because when you do that limit, what's that going to go to? Yeah, the numerator is going to get larger and larger and larger and larger. It's going to go to infinity. So we can just go ahead and say that this diverges by the nth term test. So it does not converge absolutely or conditionally. I just wanted to put one like that on there so you could see that those aren't the only two options. It can converge absolutely, it can converge conditionally, or it can diverge, which means it doesn't do any of those, which would be the case there. All right, for this one, let's look at the absolute value of this. So you're basically just going to copy that over, but slap an absolute value around it. And all that that's going to do is get rid of this part. And what does this part do in the first place? Like, what does that mean that the series does? Alternating, not the skipping test. No, the alternating series test. Okay, it's just going to get rid of that part. So all the terms will be positive instead of alternating. So that is your absolute value of the series. So let's look at whether that converges or diverges. That's one of our special series. What kind of series is that? It's P series. P equals what? 1/2. Does that, oh wait, question. When we take the absolute value, it does, it gets rid of that part, because the only thing that that would do is make the terms go positive, negative, positive, negative. And if we absolute value it, it'll make them all positive. So yeah, that part, when you absolute value it, the alternating part goes away. Good, this diverges because it's a P series with P equals 1/2, which is smaller than 1. Yep, exactly. And this is why this is nice that this comes last in this. Well, it obviously would come last because we're going to use all of the other tests that we've done to, yeah, so it is a nice review. I'm still going to give you a study guide, but it is a nice review. So we got that the absolute value of the series diverges. So we're right here. But if the series itself converges, then we would conclude it converges conditionally. So let's just look at the series itself. We said it was alternating, so we're going to do the alternating series test. There's 2 parts to that one. Do you remember what the first part is? Good, the limit's going to have to be 0. So limit as n goes to infinity, 1 over square root of n. And will that equal 0? Yes. As n goes to infinity, the denominator is going to get bigger and bigger and bigger and bigger and bigger, so that's going to go to 0. What was the second part of the alternating series test? Good, the n plus 1's term, like the next one has to be smaller. Essentially, they have to keep getting smaller and smaller and smaller. So if you plug in n plus 1 to that, is that less than or equal to with just n? So is that true? Perfect, the bigger denominator is the smaller fraction. So this is true for n starting at 1. So we will conclude that that series converges by the alternating series test. And so our big conclusion for like the whole problem is that this series converges conditionally. So what we're looking for is, does it converge conditionally? Does it converge absolutely? Or does it diverge? I threw the first one on there as diverges because that's like always an option too. Converges, then it converges conditionally. But you always want to look at the absolute value first, because if that converges, you don't even need to do the second one. The whole thing, it will just be absolutely converges. All right, so let's try it on. Again, that's the material. Now we're just going to practice it. So let's do the absolute value of this one. And again, what the absolute value does is it just keeps it from alternating. It's going to get rid of that -1 to the power of all that mess. And it's going to make everything be positive. Oh, whoops. 1 to 1, it's 1 to infinity. Now that is also one of our special series. It isn't a P series though. What is this one? It's geometric. If you want to, you can rewrite it like this. The n, good. And it's hard, you have to be able to identify that. So will that converge or diverge? Geometric. It'll converge. R is 1/3, which is, I know, P series, well, you just got to remember they're backwards. P series needs to be greater than 1, geometric less than 1. So converges because geometric with R equals 1/3, which is less than 1. And this is the best way it can turn out. This is like, oh, happy day. Because since we got that one converges, we don't even need to do any more work for the other one. What's our big conclusion to the whole thing? Absolutely, good. Converges, absolutely. Well, you don't assume it, it's part of the theorem. Yeah, that's what it says here. So it's nice when the absolute value converges, because then you're just done. You're like, oh, it converges absolutely. All right, so let's do the absolute value for this one. And again, all it's going to do is keep it from alternating. Okay, that is not a P series and it's not a geometric series. So bummer. Those are the two easy ones because you can just basically make a conclusion. Also, because we did an absolute value, it's no longer alternating, so we can't do an alternating series test. I don't want to integrate that. So let's do a comparison, okay? Let's compare this to, actually, I'll come down to the next line here. I'm just going to compare it to 1/n, which is good enough. So this one's really weird. I actually was debating even keeping this question on here because it's really strange. Most of the time, you can compare it to something with the same powers. So for example, here, hold on, let me pause this for a second because we're going to go off on a tangent here. Okay, so good. We're going to say this diverges because P series with P equals 1, which is less than or equal to 1. So that one diverges. The one we're comparing to, I know this is really confusing because we have the series itself, we have the absolute value that we looked at, and then we did a comparison test. Okay, so there's 3 different things that we're juggling here. That one diverges. So what we want to do is say that this one diverges as well. I know I told you I always like doing the limit comparison. That's not going to work here. The only reason that works is when you get that nice canceling out, and because this one's ln and this one's n, that's not going to happen. So we're going to have to do direct comparison. So since this one diverged, we want to say it's the smaller one. If the smaller one diverges, the bigger one is going to diverge too. So we want to show that 1/n is smaller than 1 over ln of n plus 1, which it will be because n is going to be larger than a natural log. Like something linear is going to increase more quickly than a natural log. Do you guys remember the natural log graph, how it looks like this? Like it doesn't increase very quickly. It's like the lazy one. Yeah. So since this one's smaller, it diverges by direct comparison. Phew. Unfortunately, we're still not done with the problem because we found that the absolute value diverges. So we're right here. This one diverges, but the series itself might still converge. So let's go back to the original one. Now here, this one's going to be a little bit easier because if we're looking at this one, it's alternating. And so we can do an alternating series test. Okay, so 2 parts to that. We're going to do limit as n goes to infinity, 1 over ln of n plus 1. We need it to go to 0, so does that go to 0? Yeah, because n will get bigger and bigger and bigger in the denominator, so that's going to go to 0. And we need, if we plug in n plus 1, which if you put in n plus 1 there, n plus 1 plus 1, that'll be n plus 2. We need that to be smaller than this, which it will be, because again, the bigger denominator means the smaller fraction. So converges by the alternating series test. Lots of work there. What's the big conclusion to the whole thing? Conditionally, good, because this one, the absolute value diverged, and then the series itself converged. So converges conditionally. Again, there was a lot to that because we had the absolute value, we had the series itself, and because we did a comparison test here, we actually had like a third one. Actually, I think this last one I did a comparison test as well, but it doesn't turn out quite so bad. Yeah, I'll leave that question on there. I was debating getting rid of it, but that wasn't bad. We got through it. All right, last one. Let's look at the absolute value of this. Now, with all the other ones, when we did the absolute value, we kind of simplified it down a little bit after that. There's really no way to do that here, but let's just think about the sine graph real quick. It is a wave that stays in between what 2 numbers? Yeah, well, it's -1 and 1, but we absolute valued it, so we'll say between 0 and 1, but it can't get any bigger than that. So just like kind of hold that in your mind, okay? So we're looking at the absolute value for that. We're going to compare, we're going to do a comparison test here. I'll come down to the next line. We're going to compare this to 1 over n squared. So what is that one going to do? The one that we're comparing it to? It converges. Why? Converges because P series, what? With P equals 2, good, which is greater than 1. Perfect. So with a comparison test, what you're trying to say is because that one converged, the other one does too. And again, I usually like doing a limit comparison, but because this one is so wacky with that absolute value and that sign in there, we're going to have to do a direct comparison. Now, if that one converges, we want to show it's the bigger one. If the bigger one converges, the smaller one has to converge too. So we want to say that this absolute value of sine of n and all this nonsense is smaller than 1 over n squared, or n bigger than 1. And it will be true because this sine of n is going to bounce around between 0 and 1, but it'll never get bigger than 1. So it'll always have to be smaller than or equal to. Does this make sense? Like, yeah, exactly. Like it's going to have to be equal to or less than 1, and the denominator's okay. So since that is true, we're going to say that this converges by direct comparison. Oh, happy day. That means we get to be done because since the absolute value converged, our whole big conclusion to the whole thing is Converges absolutely. So yeah, I don't love those last two questions because they made me do a direct comparison and I prefer limit comparison, but you know, these are first world problems.